How's the homework? I'm confused. Yes. Oh, project. Okay. Bring that up. I will just bring it up on here. Okay. For the project, you want to make a PowerPoint, and it says, I forget what it was, this one, development. So you want to find, and I gave a few claims down here. For instance, meatless Mondays, the impact of reducing your consumption of meat will save the world. And there's quite a few articles online about it, but you want to agree or disagree with this to try and get people to agree with you. So if you believe that this will change the world, then you want to find data on it. You want a graph, you want a large value that you can humanize. But you want to do a slideshow explaining why people should agree with you. And if you want to do, if there's something you believe strongly about, as long as it has to do with sustainability, then you can do it also. Just maybe send me an email or a text so I know. You're welcome. Any other questions on it? So just find a sustainability topic, and it doesn't have to be these, but these were just some suggestions I found on my own. Some were from the book. I didn't know about meatless Mondays until I started reading this book, your book. But so anything of interest to you, it could even be something you've read recently or seen recently on the news, and you want to do more research on it, and then state what you feel. Any questions on the project? Okay, and that's due Friday with 3 responses by Sunday. And there's a few people. Oh, 2. Homework. Refer to the bacteria stock flow model in figure 21 on page 154. Label each flow arrow and control arrow with the appropriate sign. Identify the feedback loop, and then whether it's amplifying or stabilizing. So page 154. So it's this figure here, and they want us to put the plus and minuses. Now, remember I gave you rules for how to decide whether it should be a plus or a minus. Now, this was the E. coli bacteria. And we want to first put the plus and minuses. Well, when we look at this, here's a spigot. When a spigot is going into your stock, it's a plus. Because this would be a blue line. The other one is our red line, which I have pink, I don't have red. Close enough. So any blue lines, if it's going into the stock, it's a plus because it's increasing the bacteria. And then if it was going out a blue line, it would be decreasing it. Unfortunately, like an antibiotic, that would be then going out, it's killing the bacteria. But in this case, we're not using one. So it's just looking at it, maybe even in a dish, how much it's generating, and none of it's dying. Now, when you're going this way, you want to think of this is always increasing in your thought process. Then is this increasing or decreasing? Well, if this keeps increasing, then these are going to keep doubling because they said the E. coli bacteria doubles every 20 minutes. So this would be a positive because as this grows, then the new bacteria grows because it keeps doubling it. Now, if this was growing and this was decreasing, that's when you put your negative. But since it's growing and then this is growing, it's a positive. Any questions on that part? So this is a feedback loop. Now, since there's no negatives, then it's amplifying. If there's an odd number of negatives, then it's stabilizing. So this one, this loop keeps increasing and increasing, it's amplifying. Any questions on that one? This was Monday. The more you do of these, the easier it's to understand what the one should be. The blue ones are easy. If it's going into the stock, it's a plus. If it's coming out of the stock, it's a minus. The pink ones are, you have to think about a little bit more. Any questions on that one?
Was there a video recording of class from yesterday?
It should be up there. I thought we'll check right now. Make a note so I remember in case. I was downloading them before my last class, but then when I got home, I don't know if I got it up. I'll check, but I did record. So, any questions on this one? The other one, let's look at the video. Friday is there. Yeah. I will get Mondays up right after class. Thank you for catching that. I know I downloaded it onto YouTube, but I must not
Thank you. I went to look for it last night. I
You should have texted me. Whenever that happens, send me a text. Don't email, because if I fall asleep or something, I won't see the emails, but I'll see the text and put it up. If I can, unless I'm not home, but yeah, I had a lot of running yesterday. It seemed like everyone needed picked up from somewhere. Tuesday. Refer to figure 25 on page 158. Each arrow is labeled with a plus or a minus sign. Describe in your own words the meaning of these labels. Okay, 158. Okay, so this one, we hadn't talked about it in class, but what it is, it's about Jimmy Carter and his wife, and they have a heating blanket. And she was always complaining because she couldn't get comfortable, even though they found a heating blanket where one heats on one side and one heats on the other, so they can control it to their own comfort. And so she couldn't figure out why she would set it at a certain temperature and his wasn't the temperature he wanted, and they kept trying to adjust it and couldn't get comfortable. He went on vacation, or not on vacation, but left for work. He was the president at the time. And when he came back, she said, I figured it out. They had switched the wires, so the control on his side of the bed controlled her side of the blanket, and the controls on her side of the bed controlled his side of the blanket. And so that's what they're showing here. Now this one is showing when they get it put on the right side, then notice, and they're not taking into account heat escaping or loss of heat, but they have the controller set and he gets the percent of heat that he wants. And then this is an increase in heat. The controller lowers or stops until it finds that it needs to start again. And so that's why this one is a negative. It's an increase in his, I guess you can think of comfortability. Then the controller slows down, or it's at the temperature it needs to be. And so this goes down until it's below whatever temperature it's set at, and then it sends more. And that's how this has stability. So this is the controller is sending heat, and then the increase in heat lowers the controller. Doesn't need to run if this is warm enough. And hers would be the exact same thing. Different temperature, but the exact same thing. Now this is when the wires were crossed, when they had the wrong controller on each side. Whatever his temperature was, when it was at that temperature, it sent the wrong signal to this one. And she sent her signal to this one. And so an increase in her heat was slowing down his controller, even the, I mean, his, yeah, controller, even though he might have had his set at, I don't know what, 79, and maybe she has her set at 85. It was getting the wrong readings, and that's what this one is showing. I forget what else we had to show. This would be a feedback loop. Would this feedback loop be positive or negative? Just this one here with Rosalind.
Positive.
Mm-hmm. Or no, it's negative. Because there's only one minus sign here, it's negative. So that's why this one is stabilized and she stays comfortable. Same thing here. It's negative, which is stabilizing because there's only one negative. This one is one continuous feedback. So this whole loop is a feedback, where this one is two separate feedbacks. And notice a negative and a negative, there's two of them, which means this is amplifying. So it keeps increasing and increasing in the heat because they're not reading them properly. And that's why they're not getting a stability or a comfort level. So this is one big loop, where this is two separate ones. Any questions on that? So the increase in her heat lowers this controller, where an increase in his heat lowers her controller. And so it's constantly amplifying and nobody's comfortable. Unless you both want it at the exact same temperature, then maybe. Any questions on that? So that was Tuesdays. We stopped here. There was a little bit more left to the section. But is there any questions before I go on? There's another one similar to what we just did, similar to the two we did for Wednesday's homework. I stuck with the same section. I thought the more practice on it, the better. More complicated effects can arise from two or more populations are connected. And we're going to do an example with a lynx and a hare from the Arctic. The Canadian lynx is a large predator cat. Lynx feed largely on the snowshoe hare. When hare are abundant, they make over 90% of the lynx's diet. So that's mostly what they eat. Because of this, a feedback loop is set up. When the hare are abundant, lynx populations grow. When lynx are abundant, hare populations decline because too many of them are being eaten. This is indicated on figure 30, page 160, where there's a positive effect control on the hare. Which was it, 160? We'll just bring it up on here. So what's happening, you have your lynx and your hare, and this is their population and their death. And I think this is a good example of being able to understand the pluses and the minuses. So we'll first look at the blue arrows. On the lynx, the births are going to increase the population because the blue arrow is going into, this is our stock. The stock, your book uses a square, and when it colors it, it's green. So it's going into the stock, it's increasing. This blue one is going out. It's a decrease in the population. So the blue arrow, if it goes into the stock, it's a plus. If it goes out, it's a minus. The same thing here. the births would increase the population, the deaths would decrease it. Now let's look at this red one. It's a plus. Well, they're all pluses, but this one's a plus. What it's saying is, as the population of lynx increase, the births increase. So as the population increases, the births increase. This is one feedback loop. And it's amplifying because there's no negatives. You need to have an odd number of negatives for it to stabilize. Now here, when the population grows, then this positive means if this grows, this increases. So as the population grows, there's more deaths. So it kind of is going both ways. When this gets large, you have more births, but you also have more deaths. Now, this is also a loop then. But this loop is trying to stabilize because there's an odd number of negatives. An odd number of negatives stabilizes. Any questions on that part? Okay. Now this lynx population is pointing here and it's a plus. So it's saying as this increases, so does this. As the population gets large, there's more hare deaths, which makes sense because they're eating them. There's more of them, they need to eat more of them. So as this increases, so is this. That's what the plus sign means. If it were a minus sign, it would mean as this increases, this decreases. So that's only with the red lines. Any questions so far? This one wouldn't, I mean, there's a huge loop that it makes. Yeah, it would go down here. I don't know. There's a lot of different loops on that one. Because you could do that one. We want this. I don't know. I would not ask for all those loops, but if we looked at all of it, there's one negative and two negatives, which means this is just going to amplify because there's two negatives. If we looked at the whole thing, this one here is stabilizing. As the hare population grows, just like the one above, as it grows, there's more deaths, but there's also more births. And that's why these are both positive. But then as this grows, it will increase the births, which then increases the population, which then increases the deaths. So then I guess you could look at this one as a loop. Any questions on that? So there's a lot of different loops you can look at when they start interconnecting these, and it kind of shows you how it's not so uniform and easily stabilized once you start adding other animals. Because if we just looked at just the hare and they didn't have anything eating them, then it would just be this circle and stabilizing. But then when you add another animal on it, things change. And this is an example of oscillating because the one goes up, then the population goes down because these are dying. So if you look at the lengths, population goes up, but then they run out of food. So the population goes down and up and down and up and down. So that would be an example of oscillating. Any questions on it? On page 161. They kept track of this. I forget. Lotka and Veltura, they simulated what it should be, and then the Hudson Bay Company kept track because of the fur trade. They kept track of how many there were of the lynx and the hare because they didn't want to completely lose them. And so they were allowed to hunt so many depending on the population. So this was an actual data of how many of each there were. The green is the hare and the blue is the lynx. And you can see how it goes up and down depending on the other one. This is what they thought it would be. And I mean, it's not too far off the data. And the blue is lower, the lynx, compared to the hare. And when it went up at a peak, then this one went up higher. So it definitely had that oscillating effect. Any questions on that? So we have an idea of how it's going to act. But this one, they were actually keeping track of it because people were selling their fur and they didn't want, kind of like the deer, you're only allowed to hunt at a certain time, but then if the deer population's too big, then you can, they'll open up more or add to it or allow you to have 2 instead of 1. Any questions on that?
It seems like this chart, these two charts make more sense than the graph does.
I agree. Sometimes they do. Once you get used to the graphs, though, the graph for this one I think was a little confusing. Because it's showing more of the interaction, and that's what's making the up and down. But for this explanation, I agree, the graph was easier. Not this one, the other graph. When you don't put anything else into play, though, this isn't too bad to look at. This was, I think it was, well, they said it could work for any population, animal, person, because as this grows, then the births grow. But as this grow, then the deaths grow. And then I think it's is it this section or the next one? I think it's the next one. They actually give us, we find a rate for these to see if they are going at the same rate. Any questions? Why does the length births decrease with hare population? 90% of the lynx food is the hare. And so if there's more deaths, if this population shrinks, then the lynx will shrink because they don't have anything to hunt. Oh, you mean this one? If this increases, then this will increase because the lynx have more to eat and causing more births. So the bigger the hare population, the more births there will be because the lynx will eat them. So that would be kind of this one here. As this grows, you have more births because they have food, which means there's more deaths because they're eating them. And that would be our loop. So sometimes you're going backward on a line. Because this is growing, there's more deaths. You're welcome. I think there was one more. Oh, overshoots. I had given you an example of the stink bug with an overshoot, and your book has one with, I think they were deer. So overshoot and collapse means it gets really large and then it collapses and stabilizes. When a population grows according to an amplifying feedback loop, but that growth depletes a finite resource that the population needs to survive. Now, for the lynx and the rabbit or the hare, they keep both becoming large again. Like as there's less lynx, then the rabbits grow more, and then the lynx grows. It's kind of like a vicious roller coaster, keeps going up and down. But in some cases, like the one here, the habitat isn't being replenished, whereas the rabbits are replenishing themselves. There was an example of reindeer in St. Matthew's Island. It's a small square mile uninhabited island in the Bering Sea off of Alaska. And in preparation for an anticipated war, the U.S. Coast Guard briefly established a base there. And what they did was they brought deer in, 29 reindeer to the island, which were never on that island. So they introduced an animal to the island, because then they thought if there was war, they'd have these reindeer to eat if they needed for some reason. And so that's why they brought them to the island. And there were no predators because these were never on the island before. So the population increased from 29 in 1944. There were 1,350 11 years later, and then 6,000 in 1962. So in almost, 20 years, almost, they grew to 6,000. However, they're eating all the foliage and the trees, and it can't grow fast enough to sustain 6,000. Maybe 29, but not 6,000. And so then as it ate all the foliage that was there was no more to eat. And so the reindeer start dying off. And in 3 years, from 1962 to 65, they went from 6,000 to 42. There was one in 1980. Oh no, one research in 1980 found none of them. No, usually what happens, there must have been no way for the forage to come back. And so these 42 didn't survive. But it shoots up and then it dropped down, and this time it went down to none. Its sustainability limit had been reached and experienced a collapse. Page 163. They show how it was working. Notice the vegetation was never increasing. So they had vegetation and it decreased because they grazed. So this is our stock, and this is our stock. Our stock of vegetation is decreasing. And as the vegetation decreases, the deaths decrease. So it's decreasing here. Now the reindeer population was increasing, then the births increase and the deaths increase. We've seen that before. But as this increases, they graze more, and grazing keeps, so that's a plus, increasing. So as they're growing more, they're grazing more. But nothing's replenishing the vegetation, so eventually it's going to run out. Notice the whole circle has 1, 2, 3 negatives, which is odd. So it should be odd stabilizes. But it wasn't stabilizing. I think this one is not in the one loop. Notice if you go this way, there's 1, 2 negatives. So that one would be amplifying. So it's amplifying the reindeer population until this is gone, and then they have nothing to feed on. So you need to make sure whatever animals are introduced into an environment, they have something that will keep growing. Unfortunately, they ate it so fast, there was none. I agree that I think the reason it's not stabilizing, if you look at this loop here, it doesn't include this negative. Like this one here, if we didn't have the vegetation included in our diagram, it should stabilize. But knowing that the vegetation is not being replenished, I think the loop doesn't include this one. So then it amplifies. This one amplifies the reindeer. But then there's no vegetation and the reindeer just die. So I think the loop works for a while as it's getting high, but then once the vegetation's gone, then this loop, you can't use it anymore because there's no vegetation and everything dies. And as you can see, it dropped really quickly. 3 years, 1962, there was 6,000 of them. And then in 3 years, it went to 42. So it took 20 years to get to 6,000, but then they depleted everything. And then 1980, there was none. Scary. Any questions on that? So they say that you should never bring an animal into a new surrounding because that surrounding is already stabilized. But as soon as you start changing one thing, it can destroy everything. Because you figure if all this vegetation is gone, there were other animals eating it and surviving and keeping it stable. And they went in and destroyed the whole system. So you need to be careful of that. Any questions on that? Now, of course, this one was brought in, it was forced, but this happens all the time. Boxes being shipped, a bug will get into one, kind of like the stink bug I explained. It came from a box from another country or California, I forget. I think it was California. I know they're in Arizona because that's the first time I saw one when I was young, when I went to visit friends. But anyways, it got into the shipping box and then it was brought here and then it multiplied like this did, like crazy. But now I didn't see any last summer. Well, maybe a couple. But they got huge. They're not to go off topic, but I mean, there were thousands in my yard, and they got into my porch when it got cold. And we had my daughter has had a New Year's Eve party every year, like from 4th grade to senior year of high school. And there's about 12 girls that come. They got into our party, like the noisemakers and stuff, and were hibernating I didn't know it. We brought it in, set up the table, put the noisemakers all over the table. And then I went back in to put some food on the table, and there's all these little stink bugs crawling out. It was terrible. Thank goodness they're not a mean or biting bug. We were able to catch them all and throw them outside in the snow. But I don't know, it just made me think of that because it was, I don't know, you see them crawling up the chair and flying through the house. And thank goodness it was before the guests got there. I don't think they would have slept over, but it happens. Now maybe I see a handful of them now. And she's been out of high school for 5 years. So they dropped fast. Any questions on that?
If a model has the same number of negatives that it does positive, does that mean it's stabilized?
No, what you want to do is look at each circle like a feedback loop. You count the number of negatives. You don't worry about the positives, doesn't matter. But if there's an odd, like if we looked at this whole cycle, there's 1, 2, 3, there's 3 negatives, which is an odd number. So the whole cycle is stabilizing. And what they could mean by stabilizing in this effect, there were no deer to start with. And at the end, there were no deer. That could be getting it back to the way it was. You could think of that as stabilizing. But for stabilizing, yeah, that's all. Just the animal, unfortunately, it didn't belong in this environment. And to me, that's what they were calling stabilizing. But yeah, just look at the number of negatives. And then if it's odd, it stabilizes. If it's even, it amplifies. So if we only use this loop here, then there's only 2 negatives and the reindeer population was amplifying. But when we add those deaths here, then it becomes stabilizing. It took this population and it made it the way it was before they came. I think that's the best way of explaining it. Correct. When you're looking at the number of negatives, it depends on what loop you're looking at. Like if we just look at this loop, there's 1. If we look at this one, there's 2. But then if we include this one, there's 3. So it depends on your loop. And when we start adding all these different ones, it makes it a little harder to see the loop. If I was going to ask you for just the feedback loop, I would make it more, let's see, is it on this page? No. Of the single ones. Like these where you can count. There's no negatives, and so it's amplifying. This one here, there's 1 negative, so it's stabilizing his temperature. Same thing here. But then like this one, unless you're using this whole loop, notice there's 2 negatives. So this is amplifying. It cannot get at a regular temperature or stable temperature like this can, because the controllers are telling the beds different things, and it won't stabilize. And you can definitely see the loop here. But this other one, there's so many different loops. There's this one, And I would not put that on a test. If I did, I would say vegetation to grazing to reindeer population to death. So then you know which one I'm talking about. But I don't think I would, I don't think I would do that. Might have you put the plus and minuses though. Vegetation grows, there's less deaths. This grows, there's more deaths and more births. So I could see giving you this and having you put the plus and minuses in, but I wouldn't have you, when there's so many different feedback loops, unless I gave you the loop, I wouldn't ask you the question if it's amplifying or not. Any questions on that? So odd stabilizes, even amplifies. This whole chart, there's 3 negatives, so the whole thing is stabilized. And by stabilize, the reindeer population that didn't belong there died out. Any questions on that? There was one more. The overshot and collapse, it's chaotic. It's a chaotic kind of behavior. Mathematics, the definition for it is a dynamic model exhibits chaos if small changes in a system condition lead to a large unpredictable change in a large long-term behavior. The deer were put into there. It was a small, what we thought was a small change. I mean, 29 deer, but then all of the deer died and all the vegetation died. So it was a long-term behavior that shot up and then came down very quickly. And it was unpredictable and a terrible situation. Weather is like that because they call it a butterfly effect. And whether small little changes in the weather could cause something big, like a cold storm is one area, warm storms in another, the two hit each other, and then you have tornadoes. So these small little effects can cause chaos or unpredictable. My nephew was going to school yesterday and his friends are sending him videos. They were pulling out of the driveway to go to their school, and all of a sudden all the tornado warnings went off, and their parents are trying to get them back home to safety while all the alarms are going off. And so it wasn't expected, but all of a sudden a tornado was spotted. I forget if it was Indiana or Illinois. His friends had moved to. But little things like that, it wasn't expected, but then a couple little changes in the weather and something big happened. Any questions on that? I always said the weatherman is one job where you never have to be right. You need to be close, but you don't have to be right. And you don't have to predict more than 3 days correctly. Any questions? Okay, so the homework for tomorrow, you should be able to do it because it's what we finished up today. I didn't want to put a new one on there. But I figured try one more similar to what we did. And if you have questions, we'll go over it tomorrow. And I will get that video up immediately.
Thank you.
You're welcome. Have a nice day.
Thank you, you too.
Thank you.
You're welcome.